We're going to begin a series of lessons on how to compute the area of plane figures. And our first is going to be the most fundamental area, figure to get the area of, and that's the area of a rectangle. You may remember the elementary school notion of what area is computing. If I have a rectangle and it is, let's say, 4 centimeters wide this way and 3 centimeters wide this way, then the area of the rectangle is how many little squares it would take to completely fill the interior of the rectangle. And that's clearly 12. We have 4, 8, 12. Each of these squares is called 1 square centimeter, which is typically written like this, 1 square centimeter, like so. And the quick way to count these squares, of course, is to multiply. This rectangle is 4 centimeters by 3 centimeters, so the area is 4 centimeters times 3 centimeters, and that gives 12 square centimeters. And we are going to take this formula as our axiom for area. There are other axioms if you're doing a formal development of geometry, but I'm not too concerned about doing all of the careful little steps if we're going to build our geometry 100% rigorously. So we are going to take as our primary area axiom the way to get the area of a rectangle, and that is we're going to multiply its 2 dimensions together. So the area of a rectangle has a base length and it has a height, and the way we get its area is we multiply those 2 dimensions together. So the area of a rectangle is base times height. This is our area axiom. It computes the area inside any rectangle. So I want to do some examples of the sort of problems you'll see about area of a rectangle. Starting with a pretty straightforward one. A rectangle has an area of 58 square inches. If one side is 5 inches long, how long are the other sides? So I have a rectangle, not sure what it looks like, so I can't really draw it to scale until I solve the problem, but there it is. One side is 5 inches long, and I know the area is 58 square inches. So since my area formula is base times height, this would be the base, this would be the height. By the way, I could have put the 5 down here. I don't really know which is appropriate, if it's the longer, the shorter. And there's no real reason to say, okay, one has to be longer than the other. We don't have a standard like the base is always longer or the height is always longer. They're interchangeable in the formula because it doesn't matter if I multiply which order these numbers in. Anyhow, back to the problem. I know the area is 58. The base is unknown. The height is 5. So I divide both sides by 5, and that's the answer. 58 divided by 5. And this would be inches. This would have to be inches, so we get square inches here. And if you don't like writing 58 over 5, this bothers you somehow, it's 11 3/5 or 11.6 inches. Slightly trickier. A side of a rectangle is 12 centimeters long and its diagonal length is 15 centimeters. What is the area of the rectangle? So now I have a rectangle. Again, I'm not really sure what it looks like, but one side is 12 inches long and its diagonal is 15 inches. So, again, I need both base and height. So I know the base is 12. I just don't know this. These are the same. This is also the height. So I'm going to use Pythagorean theorem to determine the height of this rectangle. Since this is a rectangle, all 4 of its angles are right angles, so that's a right angle here. And this is therefore the hypotenuse of a right triangle. So by the Pythagorean theorem, I can say 15 squared, the hypotenuse squared, is h squared plus 12 squared. The other 2 sides squared and added together. So this is 225 This is 144. Subtracting 144 from both sides, I get 81. Square root of 81 is 9. So the height must be 9, and again, all our units here are inches, so this must be inches. So then what's the area? Well, since area is base times height, so the area of my rectangle, base times height. I knew the base was 12 at the start of the problem. The height is 9, so this is 108. And these are inches, so this would be square inches. One final example. A pool is a rectangle with dimensions 10 meters by 30 meters. A 1.5 meter wide path is constructed around the pool on all sides. What is the area of this path? So if I think of a top-down view of this, I have this rectangular pool, which is 10 meters by 30 meters. And then around this, I'm constructing a 1.5 meter wide path all the way around this pool, like so. Let me label all the distances we know here. This is 30 meters, this is 10 meters, and then in here is 1.5 meters, 1.5 meters. All these are meters. All the way around. I want to determine what's the area of this path. Let me sort of shade it in here so it's clear. This is the area that I'm interested in determining. There are two reasonable approaches to this, and I want to show you them both. And either one of these strategies can be used in many different rectangle problems where we have shapes that are based on rectangles, but they're not just rectangles. We're going to have to pull area out or assemble the regions by piecing it together with rectangles. So one approach to this problem would be to take the area that we're interested in determining, which is this strip around the outside, the area of this path, and chopping it up into rectangles, and then computing the area of each of those rectangles and adding them together. One way to do this that's quite effective is to divide it like so. So I'm going to get the area of these 4 rectangles, and that will give me the total area. The reason this is an effective method is because these 2 rectangles on either edge are the same length, and these 2 rectangles on the other edge have the same base. So I have this rectangle twice and this rectangle twice. So I just need to figure out, based on the measurements here, what are the dimensions of these long skinny rectangles, and then I'm going to calculate their area and add them up. Well, this rectangle here is just the length 30 meters of the pool. So that's 30 meters, as is this. And since the path is 1.5 meters wide all the way around, this width right here, the width of the path is 1.5. That would be the height of these rectangles, 1.5 meters. So this rectangle here and this rectangle here, their area is 30 times 1.5. These are meters, so we're going to get meters squared. And this is 45 square meters. This rectangle is the same, so it has the same area. Now this rectangle here, its height has the 10, but it also includes the 1.5 on either side because of the width of the path. So 1.5 plus 1.5 plus 10, that's 10 plus 3. So this rectangle's height here is 13 meters, as is this rectangle's height. Each is 1.5 meters wide, because that's the width of the path. And so the area of this rectangle is 13 times 1.5 And that is, what is that? I'll get a calculator here. I don't want to make a mistake. It's like 19.5, I believe. It is 13 times 1.5. Yeah, it's 19.5. 19.5 square meters. And this is the same, 19.5. And so to get the area of the entire path, I add up these four values. So the area of the path is 45 times 2 plus 19.5 times 2, and that is 90 square meters plus 39 square meters for a total of 129 square meters. That's method one. This is a method where I take the region that I'm interested in finding and I break it up into rectangles. The second method is to view the region as a rectangle, a large rectangle, within a smaller rectangle inside removed from it. I'm going to remove that rectangle. So I'm going to be subtracting areas. I'm going to get the area of the larger rectangle, and I'm going to remove the area of the smaller rectangle. This is also a good method for a lot of problems. So looking at the measurements here, same reasoning here where we have 1.5 added on both sides. This happens with this larger rectangle in both directions. This is 30, there's the 30 meters, plus 1.5 added on either side. 1.5 times 2 is 3. So the larger rectangle is 33 meters across and 10 plus 3 meters in height. So that would be 13 meters. So the larger rectangle's area is 33 times 13. And we're going to subtract, because that gives us all this area, including the area of the pool, which we don't want. So then I have to remove the area of the pool. Slide this up a little. So I'm going to subtract the smaller rectangle inside, which is just the pool's area, 10 times 30. And that will give me the answer. Let's get a calculator out here. So 33 times 13, so 429, minus 10 times 30 is 300. And so at the end I get the same answer as I got from the other method, 129 square meters. And the strategy for which method to use in a problem like this is you have to decide which is going to require less work, which seems easier to you. Does it seem easier to take the region we're trying to find the area of and divide it up into rectangles? Or does it seem easier to you to view it as something with a rectangular hole removed, or maybe multiple holes removed? And it just varies from problem to problem. Some people prefer one method all the time. Some people prefer one method, a different method all the time. For example, if you had like an L shape, either method would be effective. You could view this as, all right, I'm going to see this as two rectangles, and I'm going to add up these areas. Or you could decide, no, I'm going to view this as a large squarish rectangle with the rectangle removed, and I'm going to subtract those two areas. Either approach will work, and you have to decide from problem to problem which you feel like is the most effective method.